Hi, stat students. Let's get started on section 10.1b, testing the significance of our correlation coefficient. So in section 10.1a, we calculated R and we made a scatter plot, right? And R is the correlation coefficient. Now we are going to test to see if there is a significant relationship between our variables. So we have a pretty good idea for R. Closer to -1 or +1 means that we are have a higher correlation. So if my R is not equal to 0, if my correlation coefficient is not equal to 0, either one of two things happen. Either the value of R is high enough to conclude that there is a significant relationship, or the value of R is due to chance. Some other variables, remember, correlation does not mean causation. So something else could be in there that could be changing things. So in order to do that, we're going to do a hypothesis test, hence the title, Testing the Significance. Before we can do that, let's talk about 4 assumptions or conditions in order to test our significance. One is we have to have quantitative data and random. We always know we're looking for random samples. The scatter plot does give us a pretty good idea that we've got an approximate linear relationship. There's no outliers. When you make the scatter plot, you get a pretty good idea if there's outliers, if you've got points that are very far away from the cluster of data or the line of data. You can kind of picture that line of best fit that we'll get into in the next section. And 4, our 2 variables, x and y, should come from approximately normal distributions. If all of those conditions are true, we can go ahead and do a test. So our null and alternative hypotheses are pretty similar to what we're looking for. We're going to use rho equals 0. Remember, rho is the population correlation coefficient. If we could calculate all R from all of the data pairs out there in the world, we would have rho. It's from our population. We typically don't have rho, but remember, in our hypotheses, we're always addressing and trying to apply our sample data to our population. H sub 1, we don't care if it's 1 or 2 tails. We just want to say that rho is not equal to 0. So if rho is equal to 0, that means there is no correlation between our variables. If rho is not equal to 0, there could be a correlation. In this case, we're going to say that there is a significant correlation. So remember, we have to do a test, though, to see if we agree with H sub 1, if we're going to reject H sub O. So there is a significant correlation between x and y. There's 3 ways to do a significance test for correlation coefficient. We are going to focus on the 3rd one, but we have some options here. I want you to be aware that there's other ways to do this. So we could do a traditional method, which uses a critical value and the t-test. We could use a p-value. We would go to the t table. Or we're going to find the critical value of R, we're going to find our critical value R, and use table 1. Nope, table I. Table I is on page 788. It's on the left-hand side, and it's a pretty small table. And I do want to make sure, well, I'll tell you in the next step. All right. So our 5 steps of testing, just like everything, our 5 steps really fall into line with everything we've been doing. We're just going to get our test statistic and our critical value and those things from different places. So step 1 is to state the hypotheses. We're not even going to identify a claim. We're just going to say either rho is 0 or rho isn't 0. Those are our options. Step 2 is to calculate our test statistic. Remember, our test statistic is R, and we probably have already calculated that. Step 3 is to find the critical value. Again, that's from table I on page 788. And there's really one important thing that I need to mention, and I can't remember where I put it, but I'll write it down. On table I, whoops, you need to remember that the degree of freedom equals n minus 2. We have two variables that can change, so we're going to remember that our degree of freedom is n minus 2. It even says it on the top of table I in case you forget. Step 4 is to make a decision. We're going to compare our R test statistic with our critical value from table I, and 5 is to summarize the results, just like always. Only summarizing the results is as simple as there is or there is not a significant relationship between, and I put the dots here so you'd remember to give me the context. There is a significant relationship or there is not, based on reject H sub O or do not reject H sub O. If we reject H sub O, that means that we think there is a significant relationship. If we do not, we don't think there is. So let's test the significance of our correlation coefficient from example 10.3. That was in section 10.1a for the number of absences in final grades. So we made the scatter plot. We felt like there was definitely a correlation, fairly strong. We found R, and I think that R was equal to negative 0.944. And that's where we ended 10.1a. So now we're going to see, is that a significant relationship? Use alpha equals 0.05. I know I put my little box here for step 4 decision. I think I have it on the next page as well. So we'll make sure we revisit that. All right, so step 1 is to state our hypotheses. Either there is no correlation or there is a correlation. I don't care if it's a positive or a negative correlation, I just want to know if there is or is not. Step 2 is to find our test statistic, which luckily we already did, and we found was a negative 0.944. Step 3, we're going to go to table I on page 788 with our degree of freedom of 7 minus 2 because we had 7 pairs of data. So degree of freedom is 5 and alpha is 0.05. If we do that, our critical value is equal to 0.754. So we need to know what this means. So I want to tell you. So what we're going to do is I'm going to think about that R. Remember, R can go from positive 1 to negative 1. 0 means there's no correlation in the middle. My critical value is technically positive and negative. So I'm saying, all right, if this is 0.754, any test statistic or R value that fell between 0.754 and 1 is reject. Negative 0.754 critical value would be a reject. So if you like to picture it, you just think to yourself, well, where does 0.944 fall? It would fall here in that negative side, so it would be a reject. If you like just a little table to tell you, we can say if our absolute value of R is less than our critical value, we do not reject H sub O. If our absolute value of R is greater than, if our absolute value of R is greater than or equal to our critical value, so if our R fell right on that critical value line, we are going to reject H sub O. So if you're visual, picture it that way. If you just like a rule, remember you're dealing with the absolute value because the critical value doesn't care if it's positive or negative, so we just use the absolute value, the 0.944. So that means for our case in step 4, if we're going to compare our absolute value of R to our CV, so 0.944 to a 0.754, that means our R is definitely greater. Since our R is greater, we are going to reject H sub O. If you're a visual person, it fell into that rejection shaded area. If I'm rejecting H sub O, that means I do not like it, which means that I think that H sub 1 is true. So for step 5, If P is not equal to 0, that means I believe that there is a significant relationship between the number of absences and final grades. And that is a hypothesis test. So let's talk about one last thing, which is if we do find a significant relationship. So correlation and causation. So things can be correlated. We can see a correlation, but we can't necessarily say it's caused by that. So when we reject H sub O for any alpha value, by the way, table I only has an alpha of 0.05 and 0.01, so pretty limited on what you're going to use for your critical value. Here are the possibilities that can exist if H sub O has been rejected. The relationship is cause and effect. It is. It's a correlation. It's definitely a causation. It could be reverse or inverse, indirect cause and effect. The relationship could just be a fluke, and there could be some other variable in effect that is making this happen. Remember, way back at the beginning, we talked about confounding variables. Or it could be not just a third variable, but it could be complex and affected by many variables. So there could be kind of almost coincidence, something else is making this happen, or it could be just a coincidence. So caution at the end of section 10.1b. Keep in mind, even if we find a significant relationship, we do need to have some reservations before we just jump on board and say, well, that correlation is causation, because there could be other factors. It could be, but it might not be. So my caution statement to you is that correlation does not automatically mean causation. More investigation is necessary. That is it for section 10.1b. Thanks for hanging in there and have a great